And the screen sharing number 2. Okay, so today we will be taking a look into the more complex variant of C, namely C++, which is, in contrary to just C, a object-oriented language. This means that you can create, that you can not just use simple machine types, but you can, or structures, which are pretty much just a simple abstraction of a memory block, but you can create complex objects with own program logic and even so-called inheritance, in which we will take a look shortly. So let's start by creating a new project. And we will again create a simple console application for our testing purposes. Okay. Good. So we have our new project, and let's just start outright with our first object. So it is customary to break objects up into two files, one which contains all the definitions, which is called the header, and one which contains the actual program logic. So we call it my class H for the header, and we create a source file, my class CPP. A C++ file must have the ending CPP, of course, otherwise the new features will not be enabled and you won't be able to write C++ code inside it, obviously. One thing you might notice is here that the compiler automatically added this definition at the top. This preprocessor definition ensures that if we would to include this file multiple times, effectively it would only be included once. Before that, in the time of just C, the typical method to do it manually was to just use the preprocessor as well, but in a much more simple way. So you first inside your header define something like my class, and then since you knew how this would be called, you made an if hash if def, if ndef. So if not define my class, then you have here your definition. Then you made an end if at the end. So if the file would be included twice, the first time it would not find my class, so it would define it and define everything else. And the second time it's included, it would see that my class was already included, and then it would not define anything. Such a situations where you have a file included multiple times can arise if you have different headers for some more complex things, which then on their own include some things, and then you want to include one of those headers and then another header, and both headers may have the same dependency, so in the end both will include some third header. And in this scenario, either by using pragma once or by using this preprocessor trick, you can ensure that the first of those headers you actually need that is included will include the primary dependency header, and then the secondary header which is included later, which would want to include the already included header, will effectively not do it since it already is included and all the definitions are available. Okay, so but that said, since we have more than C++, we don't need this, and we just start outright with a class. So similarly to structs, you just start with the keyword class, then you provide a name, C my class. It is customary to start classes with a capital C, but that's just a convention, so you are free to not follow it if you want. And the main difference, if you have a C++ compiler between how a struct object and a class object is handled by the compiler, is that the struct object by default, everything that's in it will be treated as public, while in a class, everything that's in it by default will be treated as private. What does this mean is we will see in a second, but let's first start with defining a constructor. A constructor is a function which is invoked when the class is created, and it has the same name as the class itself. And then, so basically, while in C we used malloc to create objects, or rather to allocate the memory for objects which didn't need creation as they were simple. In C++, objects might not be simple, and it is customary to use the new operator. Although in principle you could use malloc to just allocate the memory and then call the constructor on the provided memory block, which would then execute the remaining initialization. But such shenanigans would be really only needed in very special cases where you want to manage your application's memory, even for the classes, and usually that is not necessary. So for now we will just stick to using new, and of course instead of using the free function, we need something else, which is in C++ called delete. And the difference between the main difference between freeing something and deleting an object is that if you call free on the memory object, it will just release the memory and not do anything else. While if you call delete on a C++ object, it will invoke yet another function called the destructor, which has almost the same name, just preceding that with a tilde. So that's the so if you have some more complex objects which want to allocate some more memory at the beginning, or initialize some strings which might in turn allocate memory, etc., then you can do this here. And then of course in the destructor you can release all the memory that you have allocated manually yourself. And the next fancy feature is that if you would to include some variable, we'll declare this variable as private, and we'll include another include string. Oops. So std is a namespace which contains the standard template library templates, and one of those templates is a string, which is very convenient since it does all its own memory management, as we said during one of the last lectures when we talked about strings. Normal C strings are quite limited in what you can do with them. Using std strings or any other more advanced custom implemented string class makes working with strings very convenient, and from the look and feel much more how it behaves in higher languages like Python, Java, JavaScript, etc. So we define here our m string, and this string, being a class, being an object, it has an own constructor and an own destructor. And the nice thing is that we don't need to call those explicitly. The compiler will create all the necessary calls for constructors and the destructors of the member objects of our class completely on its own. One thing we should change is that we want to have only the definitions in our header file. Now if we would have a very simple function like just returning a value or something, we can of course put it here, but it is a better practice to keep the program logic, especially once you start writing more complex classes, separately. So for example here in our my class CPP, first thing we would do is to include of course our header, my class H. And then if we want to define a function which belongs to a class, we use this double point operator. So first there comes the name of the class, then comes the double point operator, and then comes the name of the function of that class which we want to implement. For the destructor we do the same thing, and we will add some more functions. One thing you may notice here already is that the constructor and the destructor do not have a type. So with the other C functions we encountered until now, we had at least to specify explicitly the void type, so that there is no type. But with the constructor and the destructor giving their special functions, it is, you don't specify any type. It's just is typeless. So let's create some function which needs a type. So let's say we want to get the string as a const. That's normal thing. So char asterisk. Get C string, use a capital G at the beginning, and that's that. So we go again here, and now the type name goes. Type name directly always precedes the name of the function. So the types, first you have the types, then you have your string. And what we do here is we just return mstring.cstring, and that's a good example of a function which we actually could have put into the header, but since I wanted to demonstrate where to put the class name in case of a function with a type, then we just put it here, plus it's good practice. So that's already a first simple, very simple class. What we might want to do with the class is to add some more member variables. So let's add some something, maybe an int, just call it mint. Let's call it integer. Then let's create here another function, int get, let's call it get value. And here we will just leave it here, since it's a one-liner. Okay. So now let's start and use our class to do something. So first of all, we need to include it again. My class, the IntelliSense is quite helpful with that. And first, a class you can use. You can create a class on the heap or on the stack. So if we create it on the stack, we just create it like any normal machine type. It doesn't need any special handling. We just type the name and then my class. And here in this case, there is of course no explicit no memory allocation on the heap. It will just, the compiler will just take a portion of the stack and call the constructor internally on it. So we have the class, and now we can see what members we can access. And one thing you would notice here is that we can only access the free members which have been defined in the public section. We have no access to those which are private here. As you might remember, with the struct in normal C, we could just access all of the members. But in C++, since it's intended to be a more complex object, the idea is that you don't want the user of some given class to maybe be able to mess with any arbitrary internal state, but instead you want the user to access the class through a defined interface. So in this case we can just get a value, int value, and when we do this we'll notice that the value will be uninitialized. So let's quickly try this out, and then we will add initialization. And the second thing we'll do is before we try that, we will also try to get the string, and we will see that the string technically is initialized, although it will be of course empty. So here we have some random value. If we switch to hex view, we have the CCCC. As we said earlier, the debug heap, or generally also on the stack, the debug code is placing this special value to indicate uninitialized memory. In a release build, that often might be just 0, so you will not catch many bugs that easily. So here at this point we now want to query the string. One nice thing about C++, if you are too lazy to type very long types, and while this type is not very long, if you are working more advancedly with the different std templates, then you will notice that you might have up to 100 character long type in certain special cases. So I think since C11 there is this auto keyword, which just means the compiler pick the right type, and the compiler picks the right type. Of course, it can only pick the right type if it has some reference. So if we are taking a variable, for example, here, from a function, a return value, then the compiler just checks what is the return value of this, and then auto will be this. We cannot define a variable with the type auto without assigning something to it instantly. But in the most cases, this is more than enough. And of course, C++ being a strongly typed language, you need to have an exact type, otherwise it will not work properly. Although in this case it's just a const char. We didn't even use vchar, so it would be quite short to type, but just to demonstrate it, we used it. And what we will see here is that we will actually get a proper empty string. So this indicates that we got the string object. So you see it has a 0 inside, so it's a really nice, properly working string. It's not some uninitialized memory or something. And we can now quickly step through the constructor just to see how this all happens. But first let me disable all the stuff we always disable. So what do we don't want? Alright. Was it code generation, genau. Basic runtime checks, we don't want this. Security checks, we don't want that. We also don't want just this one. And there was one more on the linker. What was that? Yeah, enable incremental linking. No. Should be enough to get a readable code, but maybe we want to do one more thing, and that would be to actually initialize our integer with some initial value. So we go to our class here, and now there are two ways how you can do it. First of all, you can just write code in your constructor like in any other function, obviously. But there is also a second way how you can initialize things. You can specify the initialization list here. So after the constructor, you type the name of your variable, and then in brackets you can provide arguments. And you can also do it with more complex types. So for example, with our string, we could either assign it here, or we could here write string blah. And of course there is no semicolon, it just directly continues with the brackets. But since we want to show the difference, we will here assign blah explicitly, or maybe let's not use blah, let's say undefined or unknown. Undefined is nice. Actually, we could also type, it doesn't matter, it really doesn't matter, it's just a sample. So these are the two ways how you can initialize variables, or generally have code in your constructor. And now we'll run it and see how it behaves. Step through it. Okay, suck. So as you see here, it calls the constructor and it passes to it a memory address. Which is someplace somewhere on our stack, somewhere close by to be more precise. So let's do that. Click. So we have here some code which has been generated already as part of the constructor, and you see here, for example, there is a call to call the constructor of the string, which, as you see, it looks quite complicated, but most of those arguments are they have default values, so it's not a big problem for you. You can just initialize the string very simply, as we did here. We don't need to provide any of those template arguments ourselves. So it does that. Let's skip over it because inside there is a huge mess of code. And then here we have our explicit assign. First, this one where we show. It just says that it assigns to this, which we will see in a minute what that is. But here in these two lines, it overrides the integer, which is until now unknown, with 0, and then it continues to the internal code where it here again calls the constructor to create a string, and then once the string is initialized and everything else is initialized, we return from our constructor. And one thing you might notice here is that the constructor actually returns a value in rax, and the value it returns is the memory address where the object lives in memory. But since it was created here on the stack, we don't care for the return value. You also see we don't use the value in the rax register at the moment. We just continue with our code, and here then we have already our function call. So when we step into it, we just end up simply in the function, which, as every simple function, saves some arguments to the stack, and then well, actually it doesn't save anything because we don't provide the arguments, but if we would, then just does its thing, returns a return value, and then returns to where we came. And the other one is just as simple as the first one, so we don't look onto this in detail yet. But the first thing we need to add here will be some ability to set the value. So we use a void function, set value, and so if you want to allow the user of your class to set the value from externally and not as a effect of an internal process, then you can do it with such a setter function. And one more thing which we can do here is we can define the get function as const, which has the implication that inside the function's body we are not allowed to modify any of the member variables of our class. And similarly like any other const specification which we already had a look on in the recent lectures, you can overwrite it by using typecasting and then still change. So this const is a guideline and the compiler will try to enforce it, but if you intentionally want to work around it, you can. There is nothing in the mechanics how const is implemented to stop you from doing that with the right typecast. So at this point it's still very early in in the explanation of how classes work, but the most important thing to take away at this point is that it's like a struct, but it has functions. And those functions, as you can see here, can access all the variables which have been defined on our object as if they would be local variables. And one more thing one more thing to show. Inside a class you have another variable which you don't see called this, which basically is a pointer to the class itself. So whether you access just mstring or access this mstring, it is the exact same thing what you are doing. You are accessing just member variables. This is not really useful if you want to access member variables, but it is very useful if you would want to call some function and pass your own address to that function. So you can do it with this variable. So this comes in handy here in various cases, and of course we need to keep the same type limitation. So if we define this as constant, we of course need to make this const as well. Okay, so that much to classes created on the stack, and we can of course do the same and create a class on a heap. So we just make asterisk p for pointer. Of course the names are arbitrary, but it's customary to start with p if you have a pointer, and then we type new class, and then we have a class created, set value 0. Let's go with something more interesting. 1, 2, 3, get value 1, 2, 3. And if we step through this constructor, we will see that there will be a allocation executed on the heap, and then this memory will be used. So we have here a call to the new operator, and then we have a call to the actual constructor, which then as an argument gets the address which has been returned by the new operator, and the rest behaves the exact same in the exact same way. So we will not step through that. And of course, once we are done using our class, we need to not forget to delete. Oops, 1 E too much. To delete it, because otherwise, of course, we will have a a dangling pointer, which is not good because it means that if the program runs for long enough time and accumulates as sufficiently many dangling pointers, then at some point your core computer will run out of memory. So this should be avoided. And since we are here also testing our other class, we can put this class into a scope. And if you have a class which is defined on the stack and not on the heap, the scope closure invokes the destructor automatically. So so at this point of complexity, the destructor is not so apparently needed, but in fact it is, because what it does when it's executed, it will execute the destructor for our string here. And this is necessary because if it wouldn't do that, then the memory which the string class internally has allocated would then become unreferenced and will just stay in the program until the program terminates. So this would not be good. We can of course here change our example to be more explicit about this necessity. So let's add just char let's call it my C string, and then here we comment this out, return a reference to our C string, and of course if we want to initialize it, we need to assign it some memory. So we can of course use the new operator also on native types. Let's make it 100 characters long, and then we of course need to fill it. Let's ps, comma, count of C string, comma, where is it complaining? Right, we cannot use count of because it's a pointer. It's not on the. We just need to write it by hand. And then of course our text that we want to pass. So what was it? Undefined, I think. Yeah. Okay. So we did this. Wait, why is it complaining? Yes. So we say destination. We say destination size. We say it wants the source size. This is a Q version of the memcopy. Okay, wait. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, and the 0 terminating character that will be. Actually, we could use string copies. Then it should at least not ask for the string copy is. So destination string. Yeah, okay, that's more convenient. At least it counts the bytes on its own. Yeah, and here of course we need to delete the C string array, otherwise it would remain accessible. And actually we can forget to delete it on purpose. We will define our const char stern string here, and now when the constructor goes out of scope, you can actually put a breakpoint here, so we see that it was called. And then we will notice that the memory in our return, so here the destructor was called. We can go back to the stack trace. We see that it's called here when the scope closes. And if we continue to our next breakpoint and then inspect string, we see that it still contains the undefined text. If we now would properly deallocate the memory, then once we arrive at the second line, it should contain garbage, and as you see, it does. So this shows the necessity of distracting your objects. So this much about that. Good. Are there any questions at this point? Or is everything clear? Everything's clear? Okay, so let's continue with our classes. So the next thing I want to show you is something called inheritance, which is the ability to create an object which contains all the properties of a parent object, or in C++ it's actually even possible to combine properties of multiple parent objects. Other languages usually don't allow for that. And then you can add your own additional parameters. To do that, we will do here a small change. We'll define those variables as protected. This means that they will be accessible by members of the derived class. And let's create a new class object. This time maybe we can use the class wizard so that we save a few clicks. It's my derived class. The file name should not contain this, and we say the base class was my class public, and okay. And the class wizard has created for us automatically a derived class. As you see, the way to do it is to specify double point, and then you write public and then the name of the class you want to derive from. If you specify the parent class as public, this means that all the members on the parent class will be available on the child class as well. If you would specify this as protected or private, then you could only call the functions which are defined directly on your child class, but you could not access the parent class directly anymore. From within your child class, of course, you could. So let's here add some functions. What would we want? We don't have a text set function, so let's go with that. It doesn't have return value. Oops. But it will need a parameter star. It cannot be const since it is supposed to modify the contents of our class. So we go here to our derived class. At this point, you might notice we have not provided a constructor or destructor for this derived class. If we don't have any members which we need to manipulate, then this is not necessary. In fact, for the parent class, if we would not want to initialize or uninitialize anything, we could also, I think, not provide a constructor at all. But since we want to do things, oops, that's a typo, we will later provide here also a constructor. So let's add a few more things. Size t string size. Oops. So here string size. The idea here is that later, if we are setting a string, we can check the needed length. So 10 len equals 10 string, so we know the length. Now if len is +1 is equals, because we need space for the terminating null, m underscore size. As you see, we can access size here. So if it's larger, then we delete mc string, and then we can make a new char of the length of length. Actually, let's do it differently. Then len +1 like this, and then we can cpy cstring s size and star. Right, this we do always. Why is it complaining? Yes, we need the s version to, oops, small s. Okay, so good, so far so good. So let's now see how this works with the derived classes. So let's change the pointer here. It's, we need to include the derived class as well. I think we have, nope. Here we have the right include already, so we can just copy it, and we can copy that and just add c before it. Yep, and then we construct a derived class, and as you see, we still have access to all the same members, plus the new ones. SetString is new. It wasn't present before, but now we have it. So we will want to do a getString. Maybe one more thing to change. Actually, we will change the behavior here. We will say that it will only allocate one character, and it will just set it to an empty string. Okay, and what we can do is we can have string 1. Then we will do our assignment. Set c string. 1, 2, 3, and then we'll get our second string, our string 2. And the important thing to notice here, or to be careful here, is that this string object, well, this pointer, it will become invalid. So even though we are getting the string 2 times, the first time we'll get a valid empty string, the second time we'll get a valid 1, 2, 3 string, but at this point, after this function was executed, this memory will no longer be valid, because inside our derived class here we have something that's more than 0, so this condition will be met, and we will here delete the existing string. So at this moment, when this line is executed, this memory becomes completely invalid, and then we are just creating a new memory block, allocating a new memory block for our new much longer string. With more sophisticated string classes, like for example the std string, then usually it allocates a memory in larger chunks as to be efficient, because otherwise, if you would add single characters, for example, to the string as some process of creating a longer string from small parts, then it would all the time need to allocate new memory, copy the old thing to the new memory, deallocate the old memory, and this would be very inefficient. So instead, it will allocate a large chunk, and then you are free to fill it up. And only once the chunk is full, it will allocate another large block, and then, well, another larger block, then copy everything over and deallocate the other one. So you might find yourself in situations where if you call c string on a std string, that you will get a pointer, and then if you add some or change the string content or add something to the string, append something to it, then the pointer will remain valid, but it's pure random, because if you would add enough to get past this chunk border and the string would internally reallocate, then your memory would become invalid. And this behavior, in a way, is something to really keep in mind, that you can write code which is wrong but which works, and which will only fail in very specific scenarios. So it's important to keep in mind, to track in your mind the code which you are using, and understand where memory reallocations might occur. With regard to C string in particular, and its C string, with regard to the std string in particular and its C string function, it is good practice to never assign the function's output to a variable. Just use it as an argument for some other function, because usually this other function, internally, whatever it does, it will not affect your original C string. So within it the memory reference will always be valid, and once you exit the function to do something else, then you don't have an explicit variable where you might have accidentally held on to a invalid value. Of course, you might be very lucky such that the memory gets reallocated and at the same offset as we have seen with realloc. This is possible, but this is not something one should rely upon. Okay, so here we see that the first reference is of course invalid, and the second reference contains attest123, and to hammer the point in, we can put a breakpoint here and see that here the string is valid. It shows properly that it just contains nothing. We can go to its memory location here, and then if we step over the internal function, the content of the string was just filled out with TDD, indicating that memory was deleted, and at this point we need to get the new pointer from our class. Okay, so first of all, is this clear until now, or should I elaborate on something in more detail? Because everything that follows from this point on is based on this understanding of the object nature of C++. Can you hear me? Someone wrote something into the chat. Okay, yeah, someone wrote that they can hear me, so I guess it's fine. And someone also asked a question about the header thingy. So important thing, just speak out loudly. Don't be shy and write in the chat, because I'm not watching the chat. So the question in the chat was, what's the difference between this pragma and using this preprocessor definition strategy? Functionally, they do the same thing. Pragma once is more modern, and it's less typing. So whenever you want, you can use it. There is one thing to keep in mind, that this pragma once does not work if you include the file in a C file. So if it's not a CPP file, just a C file, then pragma once will not work. But at this point, it's also important to know that if you have any classes or objects defined in your header file, then this will also not work. So if you are writing a header which only contains code which is compatible with plain C, then it would be advisable to use the old style. And if you are writing a header which contains classes, then just stick with pragma once, because that saves you on typing. Okay, so let's continue. So as we know, this class here is derived from this CMY class, and now an interesting thing would be to see what happens if we try to assign a pointer that points on the derived class to a pointer which is supposed to point on the parent class. And as you see, the compiler is in fact not complaining, and in fact it is working just fine. Just that here now we only have those functions available which we had available before on the parent class. We cannot access the objects that belongs to the more complex derived class. This is already an extremely powerful mechanism, because it allows you to pretty much extend any class you might want to extend, and then all the functions which are just taking the parent class as argument will still be perfectly fine taking your extended class as an argument as well. And the way this works internally is that when the memory is allocated for the new object, it just first allocates the memory for the parent object, then it allocates the memory for the current object. And of course, if you would have multiple parent objects, so there is no official limitation to how many derivations you can have. So from our derived class, we can have a derived class, and from that one a derived class, and so on. Practically, probably at some point the compiler will throw some sort of cryptic error saying that it cannot handle so many derivations. But this is not part of the standard. It's just up to the compiler implementation. So another limitation one might run into at some point is the amount of member variables that you can put into an object. There is no official limits in the standard specification, but practically at some point I actually ran into that once, but I think that was at about 1,000 and something member variables. So the limit is pretty high, and that was like 20 years ago. So modern compilers may have increased the limit by an order of magnitude. I have not tried to recreate that at any point, but that might happen. And the simplest thing in such a situation really would be to just split it up into two objects, and then have an object which contains both objects, and then it's fine. It might need to contain them as a pointer, but these are more practical limitations which realistically most people will never hit. So, but it's good to know that such limitations which are not part of the standard in the reality of course exist. And that's that. So just for good measure we can maybe derive a second class from that, just to demonstrate it. Derived 2 derived 2, let's call it just derived 2. Actually maybe we should call this just derived 1 and then the other one derived 2. So of course now we need to change here to derived 1 and then here to derived 1 as well. And in the derived 2, what do we want? Clear string. Let's make just a function which just clears the string, which effectively is we just delete it and then put null into it again. Sorry, this should be derived 2. Suck. Okay. Right, so yeah, we could at this point create a derived 2, assign it to derived 1, and then assign this to the base class. As you see, assigning in this direction works just fine. What doesn't work fine is if you try to assign upwards the inheritance chain. So let's call this pointer 1. Now let's try to make a derived 2 class out of our class 1. So at this point, what they broke here, pointer 1. So at this point it's important to notice that we have created a derived 2 object. So all the memory which might be needed, now in our example of course we haven't added new members. So a class derived 2 and a class derived 1 and the class my class, they have all the same size yet. If we would have added some member variables or do some other things, then the size would change. But we haven't, so technically they would be castable even by force, but the compiler is not smart enough. It does not inspect the code deeply enough to understand that. It just knows that the type of class is derived 1, so all the all the parent classes are fine. All the derived classes, it doesn't know. It's up to the developer. So you can of course force the casting by using the cast operator, and in this case it will work. But if in fact even if you would have created here a derived class 1 or just a base class, it would still work, as said, because we don't have any additional variables. But as soon as we introduce additional variables, then such a cast would be very bad, because it would make subsequent code probably use memory regions which are invalid. So let's maybe add some variable to our class 1. Ball m, we'll make it read-only, and at this point we'll need a constructor. One thing to note is that you can in fact add arguments to a constructor. So we have not done that yet, but maybe we should quickly extend our base class here with some arguments. We'll just make a const char stern init is equals null. So we can also provide a default value like with other C functions. And now in our implementation, we of course need the argument, and then we can here change this so if there is some initializing value, then we do that. And let's call it string for simplicity. So this is, well, highly improvised, so to say, because obviously it would be much more elegant to have a function that can assign the code on a parent class and stuff like that, but here this is just as a simple demonstration. But let's return to our my class here. So we have here our read-only variable, but let's maybe so a boolean will be internally just either an int or a character depending on the compiler preset, but it's so it will not be directly apparent if it's filled with uninitialized value. So maybe we should just make it an int and then assign 0 or 1 to it, and then we'll see that it contains garbage if it is not initialized. Okay, so we do this, and we have this here. The function for read only will just be to make this not work. If read only, then return, and don't do anything. So at this point, we can, for example, for the purpose of the demonstration, use here the object which is derived on the stack. We just need in its address. As you see here, we use the dot operator, while here we use the arrow operator because this is on the stack and that's just a pointer. So here, to do a cast, we need to get its address, and maybe actually we should add 2 more functions. Set read only. And or is so it's customary if you have getter functions which return you a boolean to call them not get read only but is read only. Just sounds a bit better, but it's of course up to you which nomenclature you choose, since that's not part of any standard. Okay, so we are here, and on this function we will first try to get sorry, is read only for test 1, and then we'll try to set read only. What we also could do is we could change the set function to actually have like set like true, have a default value, so that we can also use it to unset it. So 0, and yeah, that's that. So the first function, this one I expect to work because it will just read garbage. This one should crash, although it might work if there is some memory, some spare memory at this location. It might work, but as said, this is not what you are supposed to be doing. And we will put the breakpoint here. Okay, something's complaining. Right, we already have a pointer 1. I wanted to call it pointer 2. Okay, so here, if we inspect the contents, okay, it happens that read only is 0, even though we have not set it to 0. So this should work fine. And the write, well, the write also worked. We would need some larger memory, something that will run because as I said, the memory allocation is in sizes of pages, so if it has allocated a page, but maybe what we could do is, if we re-enable the basic runtime checks, perhaps the debugger will catch the bug. Let's see. Ideally, once the memory is initially originally freed, so at this point it should raise at least at this point an exception that something was overwritten. So let's test that. Nope, it's still fine. It's not complaining. We would need to probably have some more memory which we overwrite to cause an error. If we want to yeah. Okay, here we have just made it so much more bigger so that if we run the code, it will probably overwrite something that it shouldn't. So let's try again. Nope, it's not crashing. Okay, we can try another thing. We will do this with a object on the heap. So some of the checks might not work for the stack objects. My class 1. No. Okay. We forgot to delete, so now it probably will not complain. But now if we delete it, well, if you want to provoke a crash, it doesn't work. Okay, we can make it just the memory bigger. At some point, we must be able to run into something that will not be properly writable. Yeah. How far did we went? 1e. Well, we need to overwrite 488 integers, but we found the invalid memory address. Of course, there probably was some other stuff in that memory already, so even overwriting one character might already corrupt some other state. So those things obviously should be avoided. But sometimes, if you want to crash something on purpose, it's not that easy. Okay, so this much to the basic aspects of inheritance. Now let's take a look onto something more sophisticated. So one thing that you of course might wonder is, if we here create constructors and destructors for all of those types. So let's here add also a destructor. For the demonstration purpose, you only need one, so we won't create one on the second derived object. Oops. And we'll put a breakpoint here, and we'll put a breakpoint there, and then here we have a pointer to derived class 2, and then we'll delete it. So we want to see which destructor will be invoked, and I can tell you already now it will not be the right one. Oops, we have an error somewhere. Yes, we forgot the tilde for the destructor. And in this case, as you see, when we sorry, this is for the other call, so let's quickly comment that part out. Zack. So if we here now try to run the destructor, that's not what I wanted to demonstrate. Obviously we have the one destructor. We need to have a class of type my class. here such that this does what we want. So the thing is, we have here a object of class of type myClass, but we assign to it a derived object which has another function with the same name in case for the destructor. So if we now run it, we will see pointer 1 should be derived 1. We should see that we'll end up in the destructor. Why is that complaining? Yeah, of course, because we need to cast this up, like in the case below. Yeah. Okay. Right, and still, why is that should not work automatically? So normally you are supposed to define a function as virtual for these to work. Why did that fail? Because we deleted pointer 2. We want to delete that one. So yes, success, we failed. we directly called the destructor for myClass, despite the fact that the object, when we called new, was created as a derived 2. Now, since the object here does not allocate any memory explicitly, only implicitly through the here, which is then allocated by the new operator. So here in this case it doesn't really matter, but if you would have something more complex, then of course you would want your destructor to be invoked. So what you need to do for your destructor, or for what it's worth, any function which has a duplicate in a derived object, to be invoked independently of which pointer type you have, you need to define it as virtual. So here we define the destructor as virtual, and now if we run it, we will see that we'll first arrive in the right destructor for our subclass, and then if we run it, only then the next destructor will be invoked. So it invokes the destructors like in a chain. It starts with the destructor of the most derived subclass, and then it goes up, 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 and when it's done with all of them, it deallocates the memory. And to show how this virtual mechanism works, let's add let's create those same two functions on our derived 2 class here, and let's add to it int m auxiliary value, and then we have here the same assignment scheme. So now we have a function get and set value on the derived object as well as on the parent object, and they do different things. Well, they do almost the same thing, but with different memory regions. Of course, the differences in complexity and inner behavior are up to you, so you can make them arbitrarily different. So if we go here to our example code and create a new example for good measure. So we start with type my derived class 2, okay, pointer 2. Now we will let's first create some more pointers. So we create another one, type 1, but we cast to it the pointer 2. And we don't need to really do much more, since we don't have so these functions are not defined. There is no difference on derived 1 from the main parent class, so we just need derived 1 and something that's more higher up the inheritance chain. So we have now pointer 1 and pointer 2. Both pointers have the exact same value, so we can check this by looking in the debugger. If we go to locals, and then why is that? That should have the same. Not quite, because these know the type. So if we would not have any virtual function, so let's quickly remove our destructor, then we should get the same memory address. No, it's still not okay. The compiler is doing something internally that we don't want. So let's just query the value explicitly. Void stern p1 is equals pointer 1 and p2 is equals pointer 2. Zack. Why is it working now? Now they all have as they should the exact same value as you see here. Do we run in some optimization if I remove that again? Maybe I didn't look correct. So as I said, they have, since they point to the same object in memory, they have the same value even though they have different types. You can see here that the values are identical for both pointers. I have no idea why they weren't, or at least I thought I saw they weren't during the first time I ran that. Anyhow, the type which is with which a pointer is defined with will specify set value, which function will be called. So if we call sorry, on pointer 2 we will set 2 and on pointer 1 we will set 1. And if we run the code, we will see just using the localized view that internally, even though it's the same function, derive 2, here the aux value was changed to 2 and my value was changed to 1. So it's the same function, it's kind of acting on the same memory region, but effectively that's the point, it's not the same function. If we look in the debugger, we see that here we have different function addresses because they are defined in different objects, even though they have the exact same name. And depending on the type which the pointer has, the compiler is taking the right address and the right function implementation. And now let's change this. So like here with the virtual function, we can also define those functions as virtual, but you can define any function as virtual you want. And as soon as you do this, then what happens is that there will be added a here not visible additional member to the base class, which will contain a pointer on a jump list, which will contain the final values for the virtual function addresses, which will be valid for any given object. So if we create something using new with my class, this hidden pointer will point to those functions, those virtual function addresses which have been defined on my class. If we create a derived object, what was the name of it? Derived2, then for derived2 there will be a different function pointer list, and this additional hidden member will point to this auxiliary list of function names. One thing you can see here is that we don't write virtual here. We can, it doesn't matter. If the first function that is defined is virtual, then every subsequent function will be automatically virtual as well. But for good measure, we just say it's virtual. And this way, now when we run the code, both times we will just change the value of the aux value, while the normal m value will remain at 0. So let's rerun that example. Zack. And as you see here, the way these calls work is now changed. So you see it takes some pointer, then it takes some other pointer from that, and at some point it invokes a function from a memory location. So this here shows us that the implementation is changed, so it needs more operation. So a virtual function is not as efficient as a non-virtual function, but it is much more convenient because you can override the way the system behaves. And we can prove this by inspecting our pointer here, and we see that aux value is 1, while the initial value is still 0 because it was not modified. And now, of course, you might think, okay, so let's assume you would want to still be able to invoke the original unmodified function. How would you do that? Because, for example, sorry, that was the wrong one. For example, a very common use case of these virtual methods would be to change the way one of those methods work and not completely replace it. So, for example, you would want something to happen before. So when an external caller invokes your function and you have your derived class, you might want something to happen with the arguments or with some internal state before the actual function of the parent class is executed. Or maybe the other way around. You want to get the value that the parent function the function of the parent class returned, and then you want to inspect the value and or maybe change it in a certain situation, or the sky's the limit, or maybe your imagination, so whatever comes first. So what is necessary is a ability to invoke the function of the parent class to do something with it. Of course, you could here in this particular case re-implement just the assignment to mValue, but if we would make this private, then I think we should not be able. Yeah, as you see, mValue is not offered you here by IntelliSense at all. So you cannot change, even from a derived class, the value of a private variable. But what you can do is you can type the name of the parent class. In this case, whether we choose a derived one or we choose my class, doesn't matter. So you can, if you have multiple parents, you can actually select from which parent you want to call the actual function. This is quite convenient. So this works. And of course, if you would use a derived one, that would work as well, even though the function is not defined on it, but everything that's defined on the parent is automatically available on the child. But let's maybe here actually for good measure go with using the namespace of the immediate parent, and then we can here use our get value. Actually, we don't care for get value when we're here only getting this value. We want only set value. So set value, and now both values will be set. So this allows us to be very flexible. We could, for example, actually we can make it more interesting. We can say we will always set the internal value to a number larger by 1. Why not? And then we could add here a second get value, get original value. And the get original value will just return, sorry, this goes away, and we need our class name. We will here only just invoke derived one, get value. Suck. So now in our base class we can query, let's say on the second one, obviously, get value interval 1 is equals plus, and in the second one get original value, and actually we can here add the -1 to actually get the original value if that's for any reason useful to us. So now we should in both cases get 1 as the result. Zack and Zack. So as you see, this works quite nicely. Are there any questions at this point? Okay, if there are no questions, then let's continue with something a slightly bit more complicated. As I said earlier, we can we can use we and should use the new normally, but if we want, we can use malloc as well. So let's try this. C my class stern pay class is equals malloc size of my class. Okay, so now we have manually allocate the memory needed. Now we still need to execute the constructor, and we use actually the new operator, but we use it slightly differently. We are providing it the memory and then writing let's see my class, and actually we could this time use the constructor argument which we have implemented earlier. Okay, and then do something. So f %s comma per my class get c string. That's that. And now we just need to free it. So if we want to call the destructor directly, we just do it like this. And then we need to free the memory, of course, as well. Voila. So more typing, but if you would have some own special memory allocator which you want to use for some reason, well, an actual example where you would want to use an own custom memory allocator would be if you would want to use C++ in a Windows kernel driver, because the standard new and delete operators are not defined in the kernel. So there you need to provide your own means of creating and destroying objects. So then you have the two options: either do it like this, manually allocate memory, manually invoke the constructor, then manually invoke the destructor, and then manually free the memory. Or what you also could do is you could provide an own implementation of new and delete, and then that would work as well. So which one of those you prefer is up to you. But it's just good to know that you can be very manual about those things if you want to. Okay, so we have this. Okay, one more thing that we can maybe here demonstrate is the use of so-called fully abstract classes. See my string. So we start just with a normal class, but then we define some virtual functions, and we write is equals 0 instead of just a semicolon, or instead of providing a implementation. And this means that while the function is expected to be available, the function does not exist on this object. And then let's create one more function. Actually, we can create quite a few more functions. Let's go with set c string. It's not a const. Yeah, but for now that will be enough. Okay. Is it complaining? Should not be complaining. Yes, void. Forgot the type. And now what we will do is we will derive my class from c string, and that's that. So let's see what effect this had. So one thing you already see here, the compiler is complaining that set c string does not exist on my string, and that's the main rule with virtual abstract classes, that all the functions which you have defined for the object for which you call the constructor must be defined as well. So here, if we call, I think my class 1 has it. But it doesn't have the right constructor. So here we have a different problem. We did not define the arbitrary argument here, the initialization argument for our derived 1 class. So we will need to do that. And by the way, I can show you how to invoke the constructor of a parent class. So if you have an argument which you want to pass to the constructor of the parent class, you can do it here in this initialization list, like this. And now we can create the object, since we have defined all the necessary virtual functions. And of course, if you want to add more virtual functions, you are free. You can add as many as you want, and then you can have like partially functional objects which, as they are, cannot be instantiated, but they can still provide a certain base functionality, and then which then is extended by the derived objects which you derived from your intermediate object. And one more thing to demonstrate, but let's quickly run this to see that it works. One more thing to demonstrate is what happens if you try to call what is it complaining about? My string line 7. That should be working normally. Wait, no, that's fine. The destructor, my plus here, my string. Okay, first thing we need to provide a body for that. That would have caused an error otherwise as well. Right, we need to define this as public. That's something that I often forget. I said everything in a class. So if it's private unless it's public or something else. So in this case, I forgot to set it to public, and even though this one does not have an explicit constructor defined, here the compiler complained about not being to access it. Okay, and now if we run it, zack. What did we break? Or is the apparently we broke something with printf. Apparently our return value was not right. Why wasn't that? Why was that so? Because string was not defined. It should have been defined. Let's step through it really quickly. Also, we have the we have the wrong memory size. That might already be the reason. Oops! Since I changed this here to use the derived object for demonstrative purpose, I forgot to update the size. But I think it will crash anyways. We have some other bug as well. Let's see. Let's step through both of those. So first we will check whether we will properly I didn't step properly. I should have pressed the step into button. I get zack, zack, zack. Now we are here, so we have string. We take the string length. We forgot to initialize size. That's not good. It contained bullshit data, and then of course it corrupted the memo. Oops, no semicolon there. Now it should work. Nope. What else did we forgot to set? So we are here. Initialize size to 0. We get the size. Okay, we have to step over that. We don't have the definition for string, the implementation for stringlen. Okay, so this one is something, this one is 0, so now it should work. We have not initialized this is still junk. Zack. Now we should have probably not have forgotten anything. And now if we continue, at some point, well, it didn't work correctly, it didn't print what it was supposed to print, but at least it didn't crash. So we have our class getString failed. Let's see why that failed. First let's inspect the constructor once more just to be on the safe side. Sure, because we forgot to actually copy the new string into it. That explains why the value was wrong. So first the target, and we wanted to use the safe version, so here ms size, comma, zack, string. Now we have everything. And if we step over it, it printed test as it was supposed to. So, as you see, this scheme works quite well once we have ironed out all the small bugs. And now let's add some additional functionality to our class. Let's just make a function print value. It doesn't need to be virtual. Just void print value and large p, because I like large letters, and it's a const function. So what it will do, it will just print the value of get value to string. So for printf, and then we'll print f %d \n, and we say m value is equals comma m value comma, and then we have another function get value returned %d. Did I not call it value? I called it integer. Then integer is this. Oops. Okie dokie. Backslash and makes a new line. So let's go back here. So here we create the new one. So we have normal class. Since okay, let's just ignore that demo for now. Let's make it another demo. Zack is equals new my class. Actually, we could use the above demo. That's close enough. Okay, so first of all, let's make a new demo. So we have a demo of type my class. We don't need a new value for that. Now we cannot, because we are missing here the set string. It will always complain about it. Let's just in this case move our set get clear string. Where do we have set string here? Move the set string to our main class. Zack, derived class. Set string is this one. First get and set. Okay, read only false out. We'll restore this functionality in a second. Now we can create it, so we have it. Now we can make a print value, and before that we want of course to set value 1, and when we run it, it should just print that print both values and say of course that both values are 1. Oops. As you see, they are consistent. That is what we expect. And now, when we change here to our derived class 2, then the values should be 1 and 2. 2 and 1. and as you see they are. And the reason is that when the function internally, this one here, calls get value, it also goes through the jump table that was created for this object. So even if you are inside some class and some object and you are invoking a virtual function, the control flow can get out of your parent object to your derived object, which then will be able to do something more sophisticated with your code, with the code, and then return the control flow to the parent class back. So this way it really is easy to design objects which can through derivation be customized in their behavior. One use case, for example, would even be to create some abstract object which would call some function which is not even existent on itself, and which it always expects to be defined as part of the creation process. So we have did that here, and yeah. Are there any questions at this point about this level of the derivation and the access restrictions and other object-related things? Okay, no questions whatsoever. Okay, if there are no questions, then let's maybe proceed and write something actually useful. But one more thing, which I forgot. I said we will restore the functionality of this set char, which we have removed by moving it. This read only. Since it's a virtual function, we can just here keep our check and then make set on the parent. And now we have the same functionality returned, so that we can, if you have some object which is, you can actually demonstrate this here as well. So, oops, we start with a type 2 object, yes. We set cstring to 111, then we set it read only. We cannot set it read only because we have the wrong type, so we cast. Now you obviously should not cast types just willy-nilly like this, because if you know that the pointer is of the right type, then you can, but you should usually use some mechanics to avoid such a potential miscasting. So how to do that we will look into a later lecture, but for today, where we are just investigating the very basics of C++, we will just do it the dangerous way. So we want to set it read only, and then we want to set this to enough tools, and then we want to printf get string from this, and we should see that the value will stay at 111 because after we turned it read only, all subsequent attempts to change it should be ineffective, and voila, it is 111 as expected. So I think that's that with regard to our very simple demonstrator class. So let's actually write something useful. So we create a new project, we create again a console application, we call it my list, create, voila, we don't need that, and we add a new class, add new item, sorry, not new item, new item is for files, and add class, see my list, and my list will be something with which we will work for some time, I think. So we will extend it over the course of a few lectures, probably. Or maybe not just extend, but completely rework. But let's start with it. I think it's a nice demonstrator. Oh no, I choose the name, the name my list that we already had here for the file, so we just reuse the file. So let's add here a new item, main CPP, and we will put everything into we will put main into main CPP and leave our my list for the list implementation. And here we want to actually here too we also want to include my list. Okay, so public, as we learned, we always have to first type public before we want to type our constructor in the list. So that then we create a virtual destructor. It is good practice to always create a virtual destructor even if you don't intend to use it, because if at some later point you will decide, oh yeah, I should derive that and do something with it. If you forget this destructor to make it virtual, then you might run into memory leaks when other pointers will use your derived object. So and also, given that for the deallocation, it is only used once the object is destroyed, the overhead is negligible. So every function which has not been initially defined as virtual will not go through this call table detour. So it's really fine to make the destructor always virtual. The only important thing to keep in mind is that you will have one hidden member inside your class. And by the way, we will take in one of the later lectures a look into how this behavior that we have observed today is implemented really on a low level. So what we will try to do is we will create a struct and a couple of functions that will allow us to interact with a C++ class from plain C, which as such is not object or class aware. This is possible. It's a bit hacky, but it demonstrates pretty well the low-level implementations of how these classes internally work. So we will do that in one of the later lectures. But for now, we are staying a bit more on the high level, since all this object-oriented stuff for some people is supposed to be difficult. So I think it is good if we try not to complicate things, but by taking too many tangents. I think it's more pedagogically valuable if we first take a more abstract look on the new features that we have with C++ before we then dive deep into the low-level aspects of it. So we have created here our object, and we will create a second class in the same file. So in principle, you can have as many classes in one file as you want. Of course, having too many of those in the same file will be unelegant, so try to break it up into individual files based on the function and the amount of code that you need. So if you need a very short helper class, you can put it wherever you want. If you make something longer, create a new file for it. And we'll call it my entry, which also will be virtual. And then of course it will also need to have here, no, for simplicity we could, because that one will be simple, keep everything here, and then we will make something protected, and here we will use a new function or feature of this protected mechanism, one which as such I have not yet showed you, namely the friend keyword. So using the friend keyword, you can specify either a function or an entire class which will be allowed to access your protected members. And here we will define now a few protected members, or at least one. It will be of the own type next. Okay, and our class itself. Here we'll have a also a protected member. Let's do it also protected, but it will not have any friends. And this will be just called head. So what we want to implement here is a linked list. So a list where you have well, your one object that represents the list, and this object points to the first entry in the list if there is any, and this object will then point to the next one, and the next one to the over next one, and the over next one to the over next one. They are linked, like one is linked to the next, etc. And such lists can exist in different types. So a simple linked list just has links in one direction. You can have a doubly linked list which has links in both directions. So in this case, we would have a previous pointer as well. And the advantage of such a list is that if you want to insert an element to the list, this is quite easy, because you just find the last element in the list and then append. So you don't need to like reallocate all the memory or anything like this. You just got a pointer, and then you just can edit somewhere. You will need some operations to find where the end is. And as one optimization, for example, you could have here a pointer to the tail, so to the end. Or depending on your use case, you may just say that you are happy with inserting new elements to the beginning, so you then just always insert the elements at the head. And then the next nice thing that you can do with a list is you can go through the list. So you can retrieve elements, and then the next and the next and the next element from the list. So for many use cases, you don't need to use an array which locates its objects in consecutive memory space, and then just go with pointers by incrementing the pointer by whatever your object size is. But instead, often it is enough if you create a linked or a doubly linked list, because normally you want to add elements and then you want to go through the whole list. You can of course sort it if you want, but the important thing is that such a memory structure avoids a lot of allocations. So it is quite efficient, because your objects, they can be arbitrarily complex and arbitrarily large, and this way you don't need to copy them when you are adding them to a new list. Of course, you need to keep track of the pointers, so that when you are done using them, when you remove them from the list, you also need to delete them. Otherwise, you will have again a memory leak, as mentioned already so often. And the nice thing is that about using a linked list in C++ is that you can really add a lot of nice helper functions. So, for example, you can have a variable which will keep track for the count. If you would have just a linked list without anything, then you would not know how large it is. You could count it, but this would mean to iterate through all the elements, which means some computational effort. And if you have objects, then you can just put next to your head some size. Although just the size, if you would implement the same thing just in C without in a simpler way, then you could of course have a struct that keeps a reference to the head and to the counter, and then updates the counter as well. But for our use case here, we will just go with everything C++. So we need to initialize size to 0. We need to initialize head to 0 as well, or to null in this case. Now, null, I think I already mentioned it, is just a preprocessor definition for 0. So it's just a nice thing to see. Did I say that it's a pointer? No, it should be fine. I don't know why it's complaining. It should compile. It's a pointer. I know why, because we did not include anything, and of course you need some include, which will include your the null definition. So let's go with std libh. That's a good include. So now we have our null, and in the destructor here we will add something to clean up the list. Okay, and let's see what we want. So we have our right, we should initialize this as well. The destructor is just there for good measure. We have our objects. When we want to add members, actually store data in our linked list, we'll just derive an object from my entry and add additional members to it, such that it will then get those additional fields which we can then use. But here, what do we want? What do we need most urgently? We need something to add to the list. So let's say void or insert entry. It takes something of the type entry. Stern, sorry, just a p entry. Then we would have append entry. So insert is at the head and append is to the tail, but we don't have a tail yet, so this one we will not implement yet. We want to get size. Sorry, and it is good practice to use size t for size, even if it's just counter. So size t get size const, since it doesn't change anything, return and size largest semicolon. Okay, so we have get size, we have our insert entry, and we will want a way to iterate through the list, something that is reasonably efficient. So let's for starters just make a get head function. Get head, which will return head. Yeah, and in principle we should also here have a get next, so that we can get to the next element. And here we will intentionally not make it virtual because we don't want it to be overwritable. Get next. Okay, so we have one function to implement. It's easy peasy. Zack. So per head is equals so we make a copy of head, then we assign head to be our new entry, and then heads next will be our old head. That should work. And that's that. So we have this, we have that. So let's create here a class. You can in fact create also classes inside the CPP file. It's just fine. Just that then you only can access the class from this file. So it's class. It's I called the other thing already my entry, right? My entry. Let's call it some entry, which is derived from C my entry. Public constructor. Don't care for a destructor. And here let's get with get and set string. Those two functions, some entry, zack, zack. We also need that one. Some entry that public. Why is it complaining? Const char some entry get string const should be fine. The classes of course always need to be finished with a semicolon, like everything in C, except for functions. Okay, so we have this. Actually, probably should have created a separate file for our thing here, but for now, since we only have half an hour left, let's go with that more efficient approach. So we have a C list let's define the list on the stack. My list. Now let's create some entries. Alright. Let's add it a constructor. But here, this time, since we have this thing defined on ourselves, we can be a bit more elegant about it. We of course need to set this to null, comma this 0 and this is null. But once we have those set, we can use set cstring directly here with whatever string, if we have a string. If string, then string. Right here, and we would want one more improvement here. We only delete if this is not null, although it doesn't matter. You can call delete on null, so let's leave it as it is. And yeah, string is set to size, string is copied, that should be fine. This one is null, so this will also work fine. Okay. We don't need to change anything here. One thing we are missing is that we will return null if the string was completely uninitialized. So actually we could point this to an empty string to make it initialize always. In this case, since we always expect to get something here and not a null, then we can go by without the check to keep things simple. Okay, so let's now start creating entries. Some entry asterisk p entry 1 is equals new some entry. 4 is enough. 1, 2, 3, 4. We can give it the strings 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. Actually, that's more fun. Let's do it like this: 1, 1, 2, 2, 3, 3, and 4, 4s. And now we want to add it to our list. Insert entry 1, 2, 3, and 4. 1, 2, 3, and 4. And now we will want, why is that complaining? That needs to be of this type. This is fine. We derived public. If we don't make the parent class public, then you cannot cast to the parent class type, obviously. Now we want to iterate for our list. So for entry equals list head, get head. Did we not forget something? We forgot something. We want to increase our counter, of course, so that the size, if we query, the size works. Okay, my list get head should be fine. Strich punct entry is not null. Why is this complaining? Right, because that's the return type. So that was my entry. Right here, this is not null, and then if you want to go next, it's just p entry, is equals p entry get next. Okay, and since we want to actually access the inner thingies, what we could do is either we cast it here in this line or we cast this explicitly. Let's go with casting it here. Oops. So once here asterisk and once, oops, no, that one, and once there. So since we know which type it is, casting this is okay, but of course ideally we will want to not cast upwards, downwards, sorry, not cast downwards. And now here we'll make a printf %s \n comma get cstring. Voila, and if we run it, it will just print to the output 1, 2, 2s, 3, 3s, and 4, 4s. It was too quick to see. Okay, it printed them, of course, in the reverse direction, since we are always adding at the head. If we would be adding to the tail, then it would be different. And what we now also want to do is to add a function to remove an element from the list. Remove. Actually, we can make this a boolean such that if it successfully removed the element, that it will return true, and if it failed to remove it, it will return false. So we have here, and now we can be a bit lazy and copy here our thing, but we don't have the sum entry. We'll be operating here at the level of just this thing. So we of course we don't have mylist. We could either write here this, or we just don't write anything. Yeah, let's use this for demonstrative purposes. Okay, and here inside we need to check whether the p entry has the same memory. We already used the name p to remove. Let's call it p to remove. Let's change it here to here. Actually, you can leave it. So in fact, the names that you use in your prototype do not need to match the names that you use in your actual implementation. Only the types need to match, and of course the order. So let's leave it like this. So if we find and we are happy, we can do something, and then we can return true. And if we are here, then it means we haven't found what we were looking for, so we return false. Okay. So we have the element which we want to remove, and this brings us already at the first problem, because the thing that was pointing to us already is not available to us anymore. So let's think about how we can improve that. So first of all, this is a friend, so we can here access directly the next variable, and here we don't need to use head, but we can actually access directly mhead. Yeah. Oops. Strichpunkt. So and let's get rid of this. This is ugly. And the next thing we'll do is we will change the pointer to be a pointer on a pointer. So first of all, here we need to get the pointer from the pointer. Then here we need to dereference the pointer to get the actual pointer value and check whether it is not null. I changed the name, it's pp. And now here we want to dereference the p pointer, get the error operator executed on it, and then get the reference on what the error operator returned. Voila. And one more thing to fix. Here we need to dereference the pointer on the pointer to get the actual pointer. Yeah, pointers on pointers at some point are getting complicated. Okay, so we found what we were looking for. So what we need to do is first we need to check if there is anything the pointer is pointing at. So if I'm lazy, let's just copy from here. So if there is a next thing, actually we don't need an if, we just need to copy it. We don't need an if next. So we save whatever would be the next if there is a next, because there might be no next. That might be if it's the first element to be inserted, so the last element on our list, then of course this thing will be null, but we don't know yet and we don't care. So what we do now is we take the pointer on the well, now we first need also a copy. Okay, let's just call it, let's do that. Let's call it p. Now we have that roof. It's fine. So we have our next. So what we will want to do is we will want to delete our to be removed object, and then we will want to make our pointer that pointed on the thing to be removed now point to the next thing that would be the next thing. And actually we could simplify this doing it like that, because we already have the original pointer, so we don't need to cache it. We can do it like this, and voila, that should be working. Let's try it out. So we print, then we remove, then we print again. My list, punkt, remove entry. Let's go and remove the 3 or the 4. Let's remove, the 4 is too easy. Let's remove the 3. Let's remove something from the middle. And actually then let's remove the 4 just to check all the edge cases. So always when you write test cases for your test cases, it's good practice to test also all the hypothetical edge cases. So when you will be doing some more advanced homework, then it would be a very good idea to, and we forgot one more thing, to write verbose test case. Of course we need to decrement our size variable as well. Good. Now there is one error case that is already apparent. You could in principle insert the same element to the list twice, and then if you remove it, it will get deleted. So that's perhaps not great. Of course you could change this to not delete the element. Actually we could do that using an additional parameter. Let's say by default we want the thing. No, by default we don't. We want. It really doesn't matter what we take as a default, since we are writing the code right now. The idea simply is here that we can tell the function that whether it should delete it or not, because we might want to remove it but then insert it into another list. Actually, given that, let's go with default false. And since the default is false, then we need here say true, because we want to delete it, want it to be deleted for us. And of course there is that is the next thing which we will have to keep in mind, that if we clear the list here, that then of course all the objects will become invalid. So perhaps you might want to implement a variable which can be set like the read only on the string we had earlier, and which will tell the list whether the list should dispose of its content if it itself is deleted, or whether it should just leave the things be. But that's that. Let's just run our test case. Oops. I did not click the second click. It seems it's working. It removed the 3s and removed the 4s. We can also, for good measure, remove the 1s, since I said we should test all the edge cases. The edge case where it's the first entry is also 1, so yeah. Let's see. Yep. It works perfectly. So what could we improve next on this? Yeah, let's add the on delete handling. Delete on delete sounds stupid. Delete on 3 is yeah, I'll just call it delete. So we have instead of having a function where we can set this behavior, we will have here a argument for the constructor, and when we create our list we need to tell it to take care of everything if once it's deleted. So here we have our delete. We need of course here a helper variable to keep this track of this. Snug delete and delete is equals delete, and if mdelete, then we want to delete everything, and to do that we will need something like that. Actually we could go we will need to write the loop by hand, because of course we cannot get the value from the next if we have just from the current thing once we have already deleted it. So let's start with an infinite loop. Oh, actually, no, there is a much easier trick. While head entry asterisk per entry is gleich head. Oops, I had the wrong thing in the thing. So entry is head, then head is equals entry next and delete entry. Yeah, that's a super easy and convenient implementation. So if we have something in the list, delete it and make the next thing in the list now the head, and then the thing will just loop until head becomes empty, and then we are done. And at this point, what would also be nice to have would be to have something to find an entry in the list. So this sounds reasonably useful. So let's make a find function. Find entry. Yeah, one major advantage of a design which has pointers in both directions could of course be that you could in fact remove elements from the whole list if you have a pointer to them without going through the whole list. Because if you know what's the previous element and know what's the next element, then you can restore the correct linkage directly. So this is an improvement which will need to be added. But for starters, per entry, find entry, then here we will need some search function. So ball, if you remember the syntax for function pointers, let's call it match, which will take a L and an no, it will take just an per entry and void asterisk per comma and then void Stern per param. So we will want to be able to pass a parameter which will then be passed to our match function. So let's here create the function quickly. And technically this one could be const because it's not modifying anything, but for now it doesn't matter. So let's say that here we will want to test it by killing the value. Well, let's add a few more values. Für i größer 10, Shining i++. And here we will be using std to string e. That's not the most elegant way of doing it, but since we are using C++. So what we are doing here, we are using a function which returns us a std string, which is a string representation of the number which we pass it to it as argument. And then from this object, we are calling the cstring function to get the internal buffer. And the way C implements this call is such that the object will be created as a part of this call to the constructor, and it will stay valid for the duration of the execution of the constructor. So only once the constructor was finished executing, the argument passed, the object created during the passage of this argument will be destroyed. Of course, this works with any function call, so you can in this way use transient objects quite conveniently. So here now you'll have 10 entries. Oh, and now we don't have entry. 1 through 10. Okay, so that was not the smartest thing to do. Let's restore our initial test case and just fill the list up again with new things. Print a extra long line, and we need to re-add a string because that fell victim to our Control Z. Okay, so right here. So here now we want to find the entry. So found small o is equals our list, my list.find entry. Now we need a function. In old C++, you always needed to define your functions outside of your other functions, but starting with C11, which is already over 10 years ago, so it's old enough to be assumed that it always is available. You can in fact define functions within other functions as so-called lambda functions. So you start with a square bracket, then you provide round brackets with the right argument, which would be this two. And then you need to return the right type. Return, in this case, false. And now it's only missing the parameter. So let's say we want to, as param, have a char param which will depict what we want to delete. Let's say we want to delete the entry which will have the number 6. So we can pass the parameter here. And now, of course, we need to implement the body of our lambda function, of our finder function. So first of all, we need to cast our entry to our sum entry. As you see, I'm a huge fan of copying and pasting code, which is convenient but also error prone. Now we can get the C string, and then we can str cmp _s is there no s function? Okay, then we go without the s function. Maybe it's fine enough. One, and then the other one which we want to post is the param which we got, which will need to be casted to char asterisk. And if this is null, then it means it matches. So the string compare function returns a 0 if the strings are the same, and plus or minus 1 else. And we return true here, indicating that we have a match. So this function will be invoked for every entry in our list, and it will then tell the searching function whether it found something or not. And since the function does not change things, we don't need to use this pointer on a pointer that we used before. We can just go with a normal loop. If match p entry p param, then return p entry, else. And if the loop is done without success, then we just return nothing. Now if we want to be extra performant, we can optimize out the function calls, although in a release build it is very likely that such trivial function calls would have been optimized away by the compiler anyway. So maybe for code readability it might be a good idea to leave them in, but well, I like the more manual approach. So we have found 6, hopefully. We have to check if 6. Then we print f, and since we are lazy, %s was found. This way we can change this to any other number and the message will be always correct. And now we want to get rid of it. So we use our remove function, was it here, to remove found. Obviously this is not the most let's say efficient way of doing it, because we have to go through the list twice. So ideally, if we would want to optimize things, the way we would do it would be either by providing a function find and delete, which would do both things at once. Let's see. Oh, that failed completely. Why did it fail? Is the insert didn't work for some reason. Interesting. Let's debug that. Cutscene. That's why. Talking and coding at the same time is a bit challenging. Yeah, now it worked. So we have here our full list, and here now we are missing the number 6, and 6 was found. So it worked. Where was I? I was telling something else. Right. So to optimize this, we would either have added a find and delete, which would avoid us having to go through the loop for a second time, or what we could have done would be to add something to add the second link, because then at least the remove operation would be very fast. And since this is such a great improvement, I think this would be a good homework for you. So we have 9 minutes left, so let's quickly type down what the homework will be. What's today? 11th of 5, 2023. I went too much. Add turn see my list from a single list into add a tail variable to see my list, pointing to the last and to the last first. How do we know? Well, if the head is the head is the first that you can reach, but it's the last to be inserted. Okay, let's just be pointing to the oldest, yeah, entry in the list. Although once we sort the list, the oldest will no longer be the oldest. I want to avoid, let's say maybe like this. Add a tail which pointing to the I mean, I would call it the last entry in the list, even if it's yeah, let's call it the last list. I equal the entry which in async the list, i.e. the entry which in a single linked list would have its next pointer set to null. Okay, that should be clear enough and avoid any doubt. And then add a previous to my entry pointing to the previous entry in the list. Then change insert entry to properly link the pointers together, and optional, since we always need some optional assignment. Implement append entry. Okay, so as said, inserts at the head, i.e. at the tail, to the tail. Do we want something else? Of course. We need to change. This is not optional. Change. Remove entry. Remove entry to utilize the list to move element and there is a hint for that. Mprev is null, then to mp add, but that's not explicit enough. If entry ref is null, refer to when and when per next is null, refer to per tail. So the idea is that since you are executing the function on the list itself, and you have the element which you want to remove, and you inspect the element, and you see that the previous pointer points to null, this means that the previous pointer would be, in a way, so to say, point to the head variable within the list itself, instead of pointing to the next element. So there will need to be some special case handling for within the remove function to always check whether it is as simple as just relinking the previous and next element around the one which we want to remove, or if it is at the beginning or end of the list, and thus the head or tail pointers of the list need to be updated. Okay, I think this is a good homework. This will be fun. I will upload this file and that file with a lot of more commentary to the Moodle as usual. And yeah, and that's that. Are there any questions? No questions? Okay. If there are no questions, then we are done for today. Yeah, then how's the English word for that? Successful programming. Auf ein gutes Gelingen. How I would say that in German. And if you have any questions in the meantime, you can email me at any point in time with your questions. So we'll see each other next week. Have a nice weekend. Bye bye.